So, good evening, everyone. Welcome to the week 6 live interaction session. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. So, let's start our session for today. Let me share my screen. So, good evening, everyone. Welcome to the week 6 live interaction session. I am Pratyumnan, a PhD research scholar from the Department of Chemical Engineering. I am the TA who conducts the live interaction session for every week. This course of polymer concept, properties, uses, and sustainability is offered by the course instructor Professor Abhijit Deshpande sir from the Department of Chemical Engineering, IIT Madras, under the NPTEL program. So by today's live interaction session, we have almost completed 50% of our course. So we have come across 6 weeks. So in the first 5 weeks, we saw mainly on the concepts and then the properties of the polymers. We also had few of the discussion related to its uses and sustainability. So we saw about polymers. We discussed great in detail about the chemical properties of the polymers, about the mechanical properties of the polymers in the last class. So we also saw about the elastic modulus calculation, and again, can anyone tell me what all did we see in the last class, or any buddy can recollect on what are the things that we discussed so far, just like a quick recap? Anyone? So we we primarily discussed as far as the um, mechanical properties was concerned. We saw about the tensile strength, the tensile properties, its elastic modulus, how different polymers behave when you apply stress on them. So we discussed about the brittle polymers. Then we went to something more of a, towards two extremes. We had brittle polymer, then on the other hand, or the other extreme, we had a flexible elastomer, and in between we discussed about the ductile polymers. So we also saw about how does the strain of these materials vary when when their stress is applied. So in case of brittle polymers, what happens is we need to apply a higher amount of stress for a small amount of strain to be generated, and when this stress exceeds a certain limit, these polymers break, they crack. Whereas that in case of the flexible elastomers, if you see, as much as we keep on increasing the stress, the strain also keeps increasing. So for a very small amount of stress, so for a very small amount of stress, a larger amount of strain is generated in case of the flexible elastomers or the cross-linked network structures. So we saw about the concept of ultimate tensile strength and then the toughness as well. So in case of in case of the ultimate tensile strength, the basic definition is that how much load the material can take before it fails or it breaks. So how much stress the material can actually accommodate within itself is basically its ultimate tensile strength, whereas the toughness is nothing but the energy stored, or the amount of energy that the material can store in itself before it breaks or it undergoes any failure. So what it typically means is the area under the stress and the strain graph. So that's how we discussed also that not all the polymers which are hard need to be tough. So it's a common institution that hardness and toughness are both used as synonyms, but that's not the case when we discuss about the engineering materials. A material which is hard need not be tough. So if you see in case of brittle material, they were hard, but then they were not tough because the amount of energy that the material stored is less before it fails. Whereas in case if you see for the elastomers, they are actually flexible. So they are actually flexible, but yet they are tough in nature. In case of the ductile materials also, we saw that they can actually absorb a significant amount of energy. That is predominantly because of the fact that the orientation of the macromolecules or the polymer crystals. So this is regarding the tensile properties what we discussed. But apart from the tensile strength for the polymers, there are also multiple other mechanical strength which can be tested. So one is your compression strength, then next one is your flexural strength. So we did see what each means and what each evaluates. So in case of compressive strength, we try to compress the material by using a certain amount of load, and then we see at what particular compression force does the material crack or break. Then we saw about the flexural strength, which is nothing but how much the material can bend. Then we saw about the shear strength, that is how much amount of shear force or the shear stress that the material can withstand. Then we talked about the torsion, which is nothing but the twisting of the material. So each of these tests have a different mechanism that is governing them. So that's how complex the macromolecules are. So this is something that we have been discussed since the very first beginning of the lecture, that macromolecules or the polymers that we talk about are very complex in nature, that each and every property of them are governed by different mechanisms. So continuing on that, we saw about the stretch ratio, linear elasticity, non-linear elasticity. Then we discussed in non-linear elasticity, we talked about two different models of the Mooney-Rivellin model and the non-Hookean model. After that, we went on towards understanding more about the fatigue, fracture, the failure in the material, and then we talked about the temperature as well as the strain effect, the relaxation time. So this is something that we discussed even before, the concept of relaxation, how if the relaxation is a slow process, it means that the energy is stored. I hope everybody is able to recollect. Moving upon this, we discussed about the composite formulation, why do we need to make composites, and how these composites can be useful for our final application, and the interactions between the matrix as well as that of the filler, as well as that of the reinforcement that we use. So in case of the load bearing application, we saw that the design requirement is in such a way that the Young's modulus or the elastic modulus of your reinforcement should be greater compared to that of your matrix. And the main reason why this design requirement is present is basically because the reinforcement is the one which is going to load the which is going to bear the entire load compared to your matrix. Yes, the matrix do bear some amount of the load, but then the majority of the load is borne by your reinforcement fiber. So that is the typical reason why the Young's modulus of your fiber should be, or the reinforcement should be greater than that of your matrix. So similarly, for different types of the composites that we make, the filler, the reinforcement and then the matrix will have different design requirements or the property requirements. So apart from the mechanical property enhancement, the composite formulation could also be done to increase the electrical conductivity. Specifically, what we usually do in case of storing of energy or improving the electrical properties of the polymers. So as we discussed that even though the conducting polymers have a higher electrical conductivity compared to your other insulating polymers, but still in the undoped state they behave more like a semiconducting or an insulating material. So in order to boost up their electrical conductivity, we do go for composite formulation, where we typically add nanofillers to them so that their electrical conductivity can be enhanced. Apart from electrical conductivity and mechanical properties, we also have some do this composite formulation for thermal conductivity enhancement and for improving upon the barrier properties, and for different specifications that we require, we try to manipulate this polymers using different reinforcement or fillers. So this is something that we saw till last class. So in this live interaction session, our main focus will be on few of them. First one will be the solution of the polymer solution. Then we will shift to our understanding to conducting polymers, and then their dielectric responses. So we did talk about this polymer solution previously also, but again we are also discussing this in great depth in this particular live interaction session. So speaking of the polymer solution, what we actually do is we take polymer solutions typically consist of two components. So one is your polymer coils, and then the other one is the solvent in which these polymer coils are going to be present in them. So depending upon the concentration of the polymers, we can classify them as dilute polymer solution or a highly concentrated polymer solution. The concentration which distinguishes both of them is called as the overlap concentration. So let's me write this. Polymer solutions. So first one is the dilute polymer solutions. So in case of what happens is, in dilute polymer solution, the concentration of the polymer is going to be less. So each polymer coil will be present as a separate islands, which is going to be covered with the solvent. So since the solvent quantity is more and polymer coil that concentration is less, so each polymer coil will be surrounded by solvents. However, if we keep on adding, so let me write this, polymer concentration is very less and they are surrounded by solvents. If we keep on increasing the concentration of polymers, then what happens is the polymer coils start to overlap with each other. The concentration at which the polymer coils start overlapping with each other in the polymer solution is called as the overlap concentration. Starts to overlap each other. So this concentration at which the polymer coils in the polymer solution or in the solvent start to overlap each other is called as the overlap concentration. So in case of dilute polymer solution, what usually happens is that the polymer solvent interactions becomes a major factor or an important factor that we need to discuss about. So usually the polymer as well as that of the solvent, their interaction between the polymer and the solvent typically determines their size and the shape that they will take up in that particular solvent. So when we try to, so let me write this. So the shape and the size of the macromolecule, or you can say the polymer coil, depends upon the polymer solvent interaction. So based on this, we can actually classify the type of solvent into three different varieties. One is the theta solvent, another one is the poor solvent, and another one is the good solvent. So in case of a poor solvent, or you can say bad solvent. So in case of theta solvent, what happens is the interaction, there is no interactions between the polymer as well as the solvent. In case of, so there are totally three based on their interaction, or you can say three type of solvent. One is the theta solvent, and another one is your bad solvent. So in case of bad solvent, what happens is the polymers tend to coil up, they tend to aggregate, and then they tend to deposit at the bottom. They tend to aggregate and then deposit at the bottom. That type of solvent is called as a bad solvent. Then again, another type of solvent what we have is called as the good solvent. So based on the type of polymer and the solvent interactions, the size and the shape of the macromol of the polymer coils will vary. So if the solvent is bad, they tend to coil up more and then they tend to get aggregated. If it is in case of a theta solvent, which is the ideal case, then there will be no interaction between the polymer and the solvent and they remain in the dispersed state. But whereas if you see in case of the good solvent, what happens is these polymer coils tend to expand. So there is an expanded coil state, or even if the water molecules or if the solvent molecules, water in whichever wherever we are dispersing the polymer coils, if they solvate, then they also can take an expanded chain structure, or like a straight they get straightened. So that structure is also possible, and all these typically depends upon their polymer solvent interactions. If we keep increasing the concentration, what we are going to gain is called as the overlap concentration, where the polymer coils start to overlap with each other. Building on the concept of polymer solution, we have to discuss about an important concept which we have also previously saw in the other lectures, that is your intrinsic viscosity. So viscosity is nothing but it basically measures the resistance of a flow of a liquid. How much resistance does the liquid uh, or how much resistance does the liquid show to flow. So intrinsic viscosity can be, again we have defined this previously also, so anyone tell me how do you define this intrinsic viscosity? Anyone? Intrinsic viscosity, we have discussed this earlier. Anyone? Anyone on what is intrinsic viscosity? We define this intrinsic viscosity, um you can say something that is related to this dilute polymer solutions. Yes, anyone? So this is related to dilute polymer solutions. So this is again, I am going to write that. So intrinsic viscosity is nothing but it is defined as, do we have an expression in the last class? Okay, that's fine. So limit C tends to C tends to 0, eta minus eta s by C times eta s. I hope now, any ideas what is eta s, C? I think we discussed this, and I hope we also discussed something called Mark-Howing equation, where we had to use this concept of intrinsic viscosity. So this intrinsic viscosity is nothing but the viscosity of the polymer solution at a very low or at very low concentration of the polymer. And here the eta s is nothing but it is the viscosity of the solvent viscosity. And the C is nothing but it is the concentration of the polymer. And the term eta minus eta s by eta s is called as reduced viscosity. So again, I hope in week 4 we discussed about this, where I showed where you can say a table listing out the different types of viscosity. So please have a look at it, because this concept of intrinsic viscosity becomes very important in case of the dilute polymer solution. And then using that only we can see that how for a very small increase in the concentration of the polymer, there is a huge increase in the viscosity of the polymer solutions. So please have a look at it. Then after this we have something so called as the persistence length. So persistence length is nothing but it is typically a kind of a it's an important parameter which discusses about how the chain orientations are correlated, or you can also say that it is a kind of a chain rigidity measure of chain rigidity. how far your polymer chain is going to be flexible or is going to be rigid is usually understood by the concept of persistence length. So measure of rigidity, or you can say that the chain orientation, it's kind of how the chains orientation are correlated. So this typically uh, speaks more about how the typically speaks more about the rigidity of the polymer chain, whether they are flexible or they are going to be rigid. So this is about the concept of polymer solution, and again this is a very basic overview, just as a kind of a recap to what was discussed in the lecture. I I can like my request is that everyone, in case if you have not watched the lecture, please have a look at the lecture, because these concepts are discussed in great detail by professor. So please have a look at it, and I hope you will be able to understand it better. So after the concept of polymer solution, we now move to the towards the concept of conducting polymers. So not all the polymers that we see are conducting in nature. A few of them among the polymers are conducting. So the major, so it is basically the electrons as well as that of the ions in the material which are responsible for the conduction mechanism. So before talking about the conducting polymers, let's have a quick discussion on the band gap of a conductor, insulator and a semiconductor. So this is something very basic, which I hope everybody would have done in their high school, in class 12th, as well as during your first or second years of your bachelor degree. So in case of a metals or basically a conductor, what happens? So the in case of a band gap diagram, if we see, there are two bands. One is your valence band, and then another one is your conduction band. So in case of the metals or the conductors, both the valence band as well as that of the conduction band will overlap with each other. So when these, so the valence band will be occupied by electrons, and then they have to actually move towards the conduction band. Since in case of metals or conductors, as we know that they both overlap with each other, the conduction usually happens without much amount of energy required to transfer the electrons from the valence to conduction band, and that is the reason they have a very high electrical conductivity. In case of insulator, what happens is these both, the valence band and then the conduction band, are separated in terms of their energy. So because of this, what happens is the electrons which are there in the valence band have to cross the energy barrier to move towards the conduction band. So because it has to cross an energy barrier greater than 3 to 4 electron volts, greater than 4 electron volts, we term these materials as insulators. Semiconductors is something that usually comes in between both of comes in between the conductor and the insulator. In case of semiconductor, both, yes, it is as everyone knows, the valence and the conduction band are separated by a band gap. However, the band gap is small compared to that of your insulator. It is typically within the range of 2 to 3 electron volts or something less than 4 electron volts. So here the the conduction of the electrons, or the movement of the electrons from the valence band to the conduction band, is not as difficult as in case of an insulator, but yes, it does require to cross the band gap or the energy gap to move towards the conduction band, and hence its electrical conductivity compared to the insulator it is high, but if you see in case of your conductors it is less. So the conducting polymers typically lies within the insulating or the semiconducting region. The undoped conducting polymers typically lie within the their electrical conductivity typically lies within the range of a semiconductor to an insulator. So usually, in case of the undoped state, they are typically in insulating or the semiconducting state, semiconducting in nature. So, in case of a semiconductor, we can actually boost its electrical conductivity through two means. So, one is either you use temperature, which we what call as an intrinsic semiconductor, or you basically use some elements to dope these semiconductors and then improve upon their electrical conductivity. So the similar concept is used in case of the conducting polymer. Since in its undoped state it behaves more like an insulator or semiconductor to an insulator behavior is observed, so it is doped so that its electrical conductivity can be enhanced. Doped conducting polymers. So okay, so this is about the doped conducting polymers, and the major reason, I mean, before discussing about the doping, the major reason why these why these polymers are conducting is basically because of the delocalization of the electrons that is present in them. So if you see majority, most of these conducting polymers are actually conjugated polymers. So conjugated polymers is nothing but they have a alternating sigma as well as that of the pi bonds. And pi bonds, or you can also explain it as alternating single as well as that of the double bonds. So these pi bonds are nothing but they are delocalized in nature. So because of this what happens is they are weakly bonded. So because of this what happens is there is a delocalization of the electron across the backbone of the polymer, and this delocalization helps in the movement of the charge carriers. So you can write this as the pi electrons delocalize which is responsible for the movement of the charge carriers. So typically in case of this conducting polymers you have some sort of a charge carriers like polarons, bipolarons and solitons. So they are typically responsible for the conduction of they are typically responsible for this conduction properties in case of the polymers. So some of the examples of the conducting polymers is One of the example is polythiophene. Of course, the first one which was ever reported is polyacetylene. Then you have doped polyaniline. Polyaniline and it's doped form, so I'll write it as polyaniline. Then you have something called polypyrrole. Then in the polythiophene family itself, you have P3HT, so that comes in the poly 3 hexyl thiophene. Then you have P dot PSS. Any guess on the full form of P dot PSS? P dot PSS is quite an interesting polymer, so we will be discussing about that. But let's go a step by step. So anyone in name about the full form of P dot PSS? So it is poly. Anyone on the full form of P dot? So very sorry again, there was an internet disruption. So yes, as I was saying, we have discussed about the concepts related to week 6 live interaction session. Now we will be going on forward the problem solving session. So in case if you have any doubts, you are welcome to ask me now, or otherwise we can proceed towards problem solving. So these are exactly the four questions that I had to discuss in the last session itself, but unfortunately at that time we did not have much time left out with us, so we will solve this off today and finish it off. So the very first question for today's live interaction session is that the is about the Mark-Howing equation. So we have also solved, I guess, two or three problems in the previous session. So even in this session, we will continue solving them. So the dilute solution viscometry data. So we have two polymer samples here. So their dilute solution viscometry data are shown in the figure, where NSP, that is your specific viscosity, divided by their concentration of the polymer solution, is plotted against the concentration. The slopes and intercepts of the plot for both the samples are shown in the figure. The plotted data for both the samples are described by the Huggins equation of dilute solution. The value of the Mark-Howing constant alpha for both the polymer sample is 0.5. We are asked to calculate the viscosity averaged molecular weight of polymer sample 1 to that of the polymer sample 2. So how do we go about solving this question? Anyone? How to solve this question? Take a couple of minutes for to think and see on how to solve. So I think the key here will be to think on the viscosity concept. So we discussed about this viscosity right now, the intrinsic viscosity, how to calculate. So I think let us actually take out the table for us. So I think now it will be kind of easy for you guys. So what is intrinsic viscosity is nothing but NSP by C when the concentration, so intrinsic viscosity is nothing but specific viscosity by concentration when the concentration of the polymer tends to 0. So I hope now it should be a bit easy. So what is the Mark-Howing equation? Anyone? Oh, Mark-Howing equation. I think with that both, if we have in hand, this question is nothing but just a mathematical what is a mathematical solving is just required. So eta, that is your intrinsic viscosity, is k times m, the power alpha. Is this fine? Intrinsic viscosity is k times m power a, where m is the molar mass of the polymer and k is nothing but the specific constant for a polymer, which is nothing, it's a specific constant which is for a particular polymer solvent system. Yes, I mean, is it correct or no, or am I missing something? So with this being in the hand, can you guys now calculate what will be the value of m? You can take the k as same because it's a specific constant for a particular polymer and the solvent. And since here the polymer and the solvent is the same, only their molecular weight is changing, we can take k value as constant. And then can we solve this problem? Yes. Is it possible? So if that is the case, then what should be the answer? This also actually comes under the family of polythiophene only, but again, since the PSS is there, I am writing it separately. Yes, anyone? So it is poly 3,4 ethylene dioxythiophene. And the PSS is polystyrene sulfonate. So if you see in case of the one of the most commonly studied conducting polymer is nothing but the polyaniline. It is one of the most widely studied conducting polymer. So polyaniline, its monomer is aniline. From aniline we actually get polyaniline. Again, there are multiple synthesis route for obtaining polyaniline. This polyaniline are typically available, or you can synthesize them in three different states. So one is the emeraldine base, emeraldine base. Another one is nothing but it is called as the penigranulin, and you have leucomerilidin. So these three states or you can say the polyaniline exists in these three forms depending upon their oxidation and reduction state, or their oxidized state and the reduced state. So in case of emeraldine salt, the polyaniline typically has both oxidized as well as reduced form. In penigranulin is a fully reduced state, whereas leucomerilidin is a fully oxidized state of polyaniline. So depending upon the oxidized and the reduced state, the polyaniline exhibit three different forms. So this is something unique about polyaniline. In case of P dot PSS, the major reason why PSS layer is present is basically to make sure that the P dot remains stable in the solvent, or you can say in water. So the P dot, usually the commercial form of P dot is in the form of an ink. So unlike in case of the other conducting polymers like polyaniline and polypyrrole, where we get monomers and then we synthesize to form the polymers, in case of P dot PSS, the commercial form is itself is a P dot PSS in the form of a ink. So the PSS layer actually provides stability to the P dot, so provides stability to the P dot in water. Again, this P dot is a electrically conductive in nature, whereas the PSS is some sort of an insulating in nature. So P dot is electrically conducting, whereas if you see your polystyrene sulfonate, its role is only to make sure that the P dot is stable. So this is electrically insulating in nature, electrically insulating. And if you see the structure, the P dot PSS actually form a type of core shell structure with the P dot as core and then the PSS as a outer shell. So since this PSS is an electrically insulating nature, it has to be removed. So people often use different kinds of solvent to remove the PSS layer, and that removal of the PSS layer helps in improving the electrical conductivity of the material of the P dot PSS. So usually upon adding the solvent, what happens is the P dot undergoes conformational changes from a coiled state to an expanded coil state, or to a more straight like chains. So what happens in that case is, in a more coiled state like we saw in the last class, the conformational disorder is more. So in a coiled state, since the conformational disorder is more, the charge are more localized, due to which its electrical conductivity is less. However, when we actually um, drop it, or you can say whenever we mix it with the other solvents, the conformation change happens. The polymer moves from a coil state to an expanded coil state, or it basically becomes expanded or straightens out, due to which there is more amount of charge localization, which improves upon its electrical conductivity. So this is a kind of way to improve upon the charge transport in case of P dot PSS. So doping is one way to improve upon the electrical conductivity of the polymers, but in case of P dot PSS, we try to apart from doping, we try to improve their electrical conductivity using different solvents. So as I said, depending upon the type of solvent and polymer interactions, the chain moves from coil to expanded coil state or to straightened chains, and this helps in the delocalization of the charges, thereby improving its electrical conductivity. Again, so majorly this conducting polymers, again if we have to talk about conducting polymers, each and every polymer is a subject of research. So even today people study in deep about polyanilines, polypyrrole, P dot PSS, how to improve upon their electrical conductivity so that they can be um, used in real life applications. But one of the major problem with these conducting polymers is they are not as flexible as that of an insulating polymer like PDMS or yeah, PDMS is the best example, or your polyurethane. So they are all they are all very flexible in nature. But in case of these polyaniline or polypyrrole or P dot PSS, that flexibility is less when you compare them with the flexible elastomers. So they are typically brittle in nature, except for P dot, which shows some amount of flexibility. Both the polyaniline and pyrrole are brittle in nature. So there are also research which are going on to improve upon its flexibility properties. So again, as I said, this is a very brief overview of the conducting polymers. Again, its mechanism is deep. So whoever is interested in conducting polymers, I would request them to read more about that on their charge carrier transport, their application, their synthesis. So it's a wide area of research in itself. So in polymers itself. So this is a very brief overview of conducting polymers. Next, we move on towards dielectric spectroscopy. So over there we typically discuss about the kind of responses that we will see for an input signal and what kind of an output signal we get. Based on that, we define the concepts of so before discussing about the dielectric spectroscopy, we see about the different type of response that we can get for an input signal. So based on that, we have something called as a linear response and a non-linear response. And in case of a linear response, we have discussed about the linear viscoelastic response. So again, this is a very brief gist that I have given for this live interaction session. I highly what do you say, recommend everyone to go through the lectures entirely so that you can get all of them in details. So moving on for today's live interaction session, the next part of our live interaction session will be on the problem solving. So our first question will be this one. Yeah. So the question is whether using this Mark-Howing equation and by knowing what is the formula for the intrinsic viscosity as it is given in the table, can we calculate the viscosity average molecular weight of polymer sample 1 to that of polymer sample 2? Alpha, again, it's a specific constant which is given for both the polymer sample as 0.5. Since it's the same polymer sample, so and it is there in the same solvent, like I mean same type of solvent, so the K value is also going to be constant for both of them. So A is constant, K is constant. You know the value of intrinsic viscosity, and from there can we just calculate the ratio of the molecular weight of the polymer sample 1 to that of polymer sample 2. But now what should be the intrinsic viscosity value? Should we take the value of the slope or that of the intercept? It is said that the intrinsic viscosity is defined as the specific viscosity upon the concentration when the concentration of the polymer or when the concentration tends to 0. So if you see the graph, the concentration is 0 at this place. So we are the y-axis here, it indicates is NSP by C. So concentration is 0. So that means the intercept is the intrinsic viscosity values. If am I correct? We have to take concentration as 0, so which is nothing but it's basically the starting of the x-axis, and at this place we have to determine the value of NSP by C, specific viscosity upon the concentration of the polymer solution. For polymer sample 1, NSP by C, that intercept is 25 centimeter cube per gram. For polymer sample 2, it is 40 centimeter cube per gram. So can we write it this way? Just a second. I'll use this space itself. Can we write? We want MV1 by MV2. Like, I mean, sorry, molecular viscosity average molecular weight of polymer 1 to viscosity average molecular weight of polymer 2. So, can we write this way? Oh. This is for polymer sample 1. So, let me keep this as M1 and M2. So it's just now we have to divide both these equations. So 25 by 40 should be nothing but M1 by M2 whole power 0.5. So M1 by M2 is nothing but 25 by 40 square. So what will be that value? Oh. So 25 by 40 is 0.625. So M1 by M2 is nothing but 0.625 the whole square. So M1 by M2 is 0.3906, or you can say 0.39. Is this the value you guys are getting? Please let me know. Any different answers, or anywhere if you are unable to understand, please unmute yourself and then let me know, so that we can see where we are going wrong. Here only one thing that you need to know is what is the value of intrinsic viscosity and the Mark-Howing equation. If you know these two, this question is just a cakewalk. So if you have any questions, please let me know before we progress towards our next question. Oh, any doubts or so let's move on towards the next question. So here what we are typically discussing is these are all kind of like the questions that we were unable to solve from the last few sessions which have got accumulated. So we first try to finish these off before we progress for solving the questions of other kinds. So let's solve the question number 6. Polyvinyl polyvinylidene fluoride (PVDF) was quenched from the melt in one case, and in the other case it was slowly cooled from the melt at 10 degrees Celsius per minute. Percentage crystallinity of the slowly cooled PVDF is 60%. The heat of fusion of the quenched PVDF is zero point 0.5 delta Hm, where delta Hm is nothing but heat of fusion of the slowly cooled PVDF, and the heat of fusion of 100% crystalline PVDF is 100 joule per gram. Percentage of crystallinity in the quenched PF is dash percentage, or we need to calculate the percentage of crystallinity in the quenched PVDF. So how do we go about solving this? We have also solved a similar kind of problem in, I think, week 4 live interaction session. So here you have two cases. One, slowly cooling. The second one is quenching. The percentage of crystallinity in the slowly cooled PVDF is 60%. Heat of fusion of the quenched PF is 0.5 delta Hm, and the heat of fusion for 100% crystalline PVDF is 100 joule per gram. Now we are asked to calculate the percentage of crystallinity of the quenched PVDF. How to solve this question? This question is quite simple actually. You just need to read the question carefully, then you guys will be able to easily solve this. Yes, anyone? Wait a second. Yes, anyone? I mean, the any ideas on the how to solve this question? So let's rewrite the information what we have in the question, and then let's see whether we can solve the problem. So heat of fusion, first I am going to write the word the data heat of fusion of 100% crystalline PVDF. It's 100 joule per gram. Now this is the heat of fusion for 100% crystalline PVDF. Upon slowly cooling the PVDF, the crystallinity percentage that is obtained is only 60%. Slowly cooling of PVDF resulted in only 60% crystallinity. Now it is written that heat of fusion of quenched PVDF is nothing but it's 0.5 times of delta Hm, but that delta Hm represents the heat of fusion of the slowly cooled PVDF. So it is nothing but zero point 0.5 times of heat of fusion for the slowly cooled PVDF. Does it make sense right now? So apart from that, we do not have anything. So with these three data in our hand, can we calculate the crystallinity percentage in the quenched PVDF? If yes, how? If no, why? If you remember in the last live interaction session, last to last, we had given this equation. Heat of fusion of slowly cooled PVDF can be written as heat of fusion of crystalline PVDF times percentage crystallinity. Can we write this equation? Heat of fusion of the slowly cooled PVDF is nothing but heat of fusion of crystalline PVDF times its percentage crystallinity in slowly cooled PVDF. Can this be written? So if this is the case, then heat of fusion of slowly cooled PVDF is nothing but it is 100 joule per gram times, sorry, times zero point 0.5, oh sorry, zero point 0.6. So 0.6 times 100 is 60 joule per gram. So this is the heat of fusion of the slowly cooled PVDF. With this equation, can so this is the heat of fusion of slowly cooled PVDF. So from here, can we calculate the heat of fusion of quenched PVDF, which is given as 0.5 times of heat of fusion of the slowly cooled PVDF as per equation 1. So using equation 1, heat of fusion of quenched PVDF is nothing but zero point 0.5 times 60, which is slow for the heat of fusion of slowly cooled PVDF. So that is nothing but 30 joule per gram. So we know this. So can we modify equation 2 similarly for crystalline materials or for our quenched PVDF? So can I write it this way? Heat of quenched PVDF is equal to heat of fusion of crystalline PVDF times percentage crystallinity in quenched PVDF. So we know the percentage, the heat of fusion of quenched PVDF now. We have the heat of fusion of the crystalline PVDF. So can we just calculate the percentage crystallinity in the quenched PVDF? And is it not that thing that they have asked us to calculate? So if you do that, then what it could be? So heat of fusion of, so it is 100 joule per gram times percentage crystallinity. So we have the heat of fusion of quenched PVDF as 30 joule per gram. That is nothing but 100 joule per gram times percentage crystallinity. So 30 by 100 is nothing but zero point 0.3. That is your percent. That is the crystallinity fraction. So percentage crystallinity will be 30 percentage. So is this fine or is this correct or anywhere any confusion, any, if you are unable to understand, then please let me know. or any different answers also, please let me know. Any questions? Is everyone getting the same answer as mine, 30 percentage? Again, if you see here, the crystallinity in case of the quenched PVDF is less. If you remember, this is what we actually see discussed when we were talking about the crystallization kinetics polymer polymers, because over there, if you remember, we discussed that when you are actually going to obtain polymer crystals from a polymer solution, we actually go for two kinds of processes. One is basically your cooling and the other one is the solvent evaporation. So in case of the first method, we discussed that polymer crystals cannot be formed if we are going for quenching method. The major reason is because rapid cooling, so there won't be enough time for the polymer chain entanglements to rearrange or to basically fold, and that is the reason polymer obtaining crystallinity in case of quenched polymers is very difficult. So that is the reason, if you see in this case, we obtained a very less crystallinity in the quenched PVDF compared to the slowly cooled PVDF. So that is the reason why it is different. That is probably the main point that we need to have in mind apart from solving the question. Why is that the variation in the crystallinity percentage? And again, that actually affects the heat of fusion. If you see in case of quench PVDF, heat of fusion is less compared to that of your slowly cooled PVDF, because percentage crystallinity is less. Heat of fusion directly relates to your crystallinity fraction. So if there are no questions in this, so let's move on to another question. Again, this is a very old question, probably week 2. So we are trying to clear all the questions in today's class so that we can start again fresh from the next live interaction session. An alternating copolymer. So it's a copolymer and the monomers are alternating here. So it's an alternating copolymer is formed and it has a number averaged molecular weight of 10 power 5 gram per mole Degree of polymerization is given as 200 and sorry 2210. The repeating units of the copolymer, one is ethylene. We are asked to calculate the next one. So how do you go about solving this question? Again, I think you will be able to calculate the weight of the repeating units, because that should be some that is, we have done multiple problems on that, so that will be simple for you guys. But after that, how we go about this? So can we write degree of polymerization times their average molecular weight of the repeating unit is equal to the number average molecular weight of the polymer? So if that is the case, can we write the molecular weight of the repeating unit as 10 to the power 5 divided by 2210, that is your degree of polymerization. So if this is the case, then So this will be nothing but 45.24 gram per mole. Now this is the molecular weight of the repeating unit, but this is a copolymer and it's an alternating copolymer, so every repeating unit is going to have both of your polymers. I'm sorry, both of the monomers. So one monomer is ethylene. What is the other? So molecular weight of ethylene molecule should be, what is the value? Molecular weight of, yes, molecular weight of ethylene, the monomer. 28. Yes. So can we write the molecular weight of repeating unit? Can we write it this way? So if that is the case, so with this as a molecular weight, now it is about a trial and error. So this question was supposed to be a multi-choice question, a MCQ with 4 options, but I have removed the option. So with the molecular weight of the other monomer being 62.48 gram per mole, you can look at what kind of monomer will be suitable and then take it as a home task, so that it will be like a trial and error basis. You can find out what is the other polymer. So with that part being a home task, if anything else is, if you are unable to understand, please let me know. If not, we can go for our last question for the day, which is 49 moles of hexamethylene diamine is reacted with 50 moles of adipic acid to form nylon 66. The number average molecular weight of the resulting polymer with the 99.5 percentage conversion of the monomer, ignoring the contribution from the N group, is. So 49 moles of ethylene diamine is going to react with 50 moles of adipic acid to form nylon. But here the percentage of conversion is not going to be 100, it's going to be 99.5. So if that is the case, then what should be the number average molecular weight? So think about this question, because this is not going to be a straightforward one. I think since we are running short of time, so let me conclude the session for today here. So if you have any doubts, you are welcome to ask me. Please let me know if you have any doubts. If not, then we can conclude the session for the day. So I think we can conclude the session for today. So I thank everyone for joining today's live interaction session. Our next live interaction session will be on 7th of September. So in case if you have any doubts, you're always welcome to email. My email ID will be available along with this presentation. So you will have access to both this presentation as well as the recording by the mid of this week. So so I would like to thank Professor Abhijit Deshpande sir as well as the NPTEL team for providing me this opportunity to interact with you all this Sunday evening from 5 p.m. to 7 p.m. So thank you and have a great weekend. Bye.